Good day, everybody. Today I want to estimate the velocity of a bullet meters per second using the values given here by Walter Lewin in his physics lecture class. He shoots a gun, and there's the time it takes, and we've got the distance and the uncertainty in the distance and the uncertainty in the time measurement. So we're going to use differentials to estimate the velocity of the bullet and the uncertainty in that measurement. So these are the values that we have. We've got the distance is 148.5 centimeters plus or minus half a centimeter, or in meters that, and then there's the time in seconds or milliseconds if you were to do the 5.8, but let's just put it in seconds. So then the velocity of the bullet is about 256 meters per second, using the distance the bullet traveled to break two wires and the time it took to break those two wires. But let's find the uncertainty, or the error, in that rate measurement. So using differentials, dr is partial r with respect to d, dd, plus partial r with respect to t, dt. And then since r is d over t, the dd measurement, or partial, is just 1 over t dd. And then the partial with respect to time will be negative d over t squared dt. So the error in the rate is basically 1 over the time times the error in the distance plus negative d over t squared times the uncertainty in the time. And to maximize the uncertainty in the rate, we will take the uncertainties so that we add two positive quantities. So the time was 5.8 milliseconds, or 0.0058 seconds. The uncertainty in the distance measurement was half a centimeter, or 0.005 meters. Again, the distance was 148.5 centimeters, or that many meters. The time in seconds squared was that. And then for the uncertainty in time, well, since this is negative, we'll take the negative value. So the uncertainty of the time was plus or minus 0.1 millisecond. So that value in seconds. And plugging in the values, we get about 0.86 plus 0.14, so about 5.3 meters per second. Or we could round it, maybe 5. So we'd say the rate is 256 plus or minus 5 meters per second. So it's a pretty decent error. And if I want to compare it to the exact, using differentials is kind of the best way to go, but just to see how differentials kind of work. If I wanted, what's the maximum rate possible that we could have gotten with our values? Well, the maximum rate of the bullet would come from if the distance was the max possible, and that would be 149 centimeters, or 1.49 meters, and the time was the minimum possible, which would be 0.0057 seconds. Right, so using the minimum time to go to the maximum distance, so that's the maximum rate given these parameters, right? So if the distance was in this range, time in that range, then the rate of the bullet at most could have been from using the max distance, minimum time, and that'd be 261.4. So it was over by about 5.4, or close to 5, over our 256. Notice that the maximum R, we used the positive delta D, right? We increased it, but we used the negative delta T, just like I did above. The minimum possible rate would be if the distance was minimized, but the time was maximized. And so that'd be, the minimum distance it could have been was 148 centimeters, and maximum time would have been that. Again, notice these two are opposite signs. That'd be like having both of these negative up here. Anyway, so that would be 250.85, or so it's under by about 5.15. Again, opposite signs needed for error. So 256 plus or minus 5, you know, does the job. If you watch the video, he does things kind of quickly, uses relative rate, the relative rate. If you put dr over r, so r is d over t, so just divide both of these by d over t and simplify. You'll get dr over r is dd over d, that's what this will simplify to, plus dt over t. And I kind of took absolute values here to get the maximum. And then the way he thinks about things, the uncertainty is time is about 1 over 60 for the relative uncertainty. The relative uncertainty is about 1 over 60, right? 58 is about 60. And here, the uncertainty in distance is about 5 over roughly 1,500, or 1 over 300. So you have a 1 over 300 relative error and a 1 over 60 relative error. Now he throws away the 1 over 300 relative error. And so in the video, he ends up with plus or minus 4 meters per second. I didn't throw it away, and you get actually an extra meter per second from that, right? But so if you do 1 over 300 plus 1 over 60, 1 over 60 times 256, you can see it's around 4, maybe a little bigger than 4, about 4.27. But the 1 over 300, it's much smaller. I mean, it's a fifth of that relative error. But when you're close to 5 or 4, you know, it's 0.8, 0.85. It adds. So with this ballpark, so this was ballpark, but you're still around a little over 5. So 256 plus or minus 5 meters per second. Again, you can watch the video. The importance of knowing errors, including them in your measurements, but also one thing he did that I don't think was right was he threw this away, and so he ends up with 4 meters per second. 256 plus or minus 4. I think you should keep it as 256 plus or minus 5. Anyway, again, differentials are everywhere. All right, so hope you enjoyed this and learned something. Thank you. Have a good day.